There is a question that almost everyone has asked at some point. If aliens exist, why haven't they come here? The standard answers are the ones you've probably heard. The distances are too vast. The speeds required are beyond any conceivable technology. The energy costs are prohibitive. These answers are correct, but they are incomplete in a way that matters, because they frame the problem as a practical difficulty, rather than what it actually is in many cases, a physical impossibility. Tonight, we are going to take the question seriously, not as a cultural curiosity or a science fiction premise, as a physics problem. We are going to follow what it actually means to travel between star systems, what the distances really are in units that connect to human experience, what velocities are physically achievable and at what cost, what happens to matter and time and energy at those velocities, what the universe's own structure does to the problem, independent of any technological consideration. Because when you follow these questions carefully, when you actually do the numbers rather than gesturing at them, something changes in how the problem feels. Not the abstract sense that space is big, something more specific and more strange. A sense that the universe is structured in ways that make certain things not merely difficult, but categorically, physically, permanently impossible. Not impossible in the way that flying was impossible before the Wright brothers, impossible in the way that exceeding the speed of light is impossible, built into the laws of nature at the deepest level we understand them. Some of the impossibilities we are going to discuss tonight are technological. Given enough time and enough resources, sufficiently advanced civilizations might conceivably overcome them. Others are not technological at all. They are imposed by the structure of space-time itself and would remain in place regardless of how advanced any civilization became. Understanding the difference matters, not for practical engineering. No civilization is building an interstellar spacecraft tomorrow, but for understanding what the universe actually is and what it permits and does not permit. If you put this on because the night is long, stay. What follows will change how you think about the night sky. Not by making it more frightening or more hopeful, by making it more precisely understood. And precise understanding of why alien contact is so difficult, why the universe is structured the way it is, reveals something about the nature of existence itself. Let us start with the most basic question. How far away are the stars? You have heard the answer, light years. Proxima Centauri, the nearest star, is 4.24 light years away. The nearest star system with potentially habitable planets is further. Most stars visible to the naked eye are tens to hundreds of light years away. The galaxy is 100,000 light years across. These numbers are correct. They are also, in a deep sense, not meaningful until you convert them into something that connects to human experience. A light year is approximately 9.46 trillion kilometers. Proxima Centauri, at 4.24 light years, is approximately 40 trillion kilometers from Earth. The number 40 trillion is not intuitive. Let us convert it. The fastest object humanity has ever launched is the Parker Solar Probe, which, at its perihelion, reaches approximately 690,000 kilometers per hour, about 192 kilometers per second. This is a genuine engineering achievement, enabled by repeated gravity assists from Venus that have progressively lowered its orbit toward the Sun. At 692,000 kilometers per hour, the Parker Solar Probe's peak velocity, how long would it take to reach Proxima Centauri? Approximately 6,300 years. Not 6,300 days, not 6,300 months, 6,300 years. More than the entire span of recorded human history from the earliest writing to the present day, twice over. This is our fastest spacecraft, the one we built with the best engineering currently available, the result of decades of work by thousands of engineers and scientists, and it would take 6,300 years to reach the nearest star. Now take a civilization we might imagine as significantly more advanced than us. Say they have managed to build spacecraft capable of traveling at 1% of the speed of light, about 3,000 kilometers per second, roughly 15 times faster than the Parker Solar Probe at peak velocity. This would be an extraordinary achievement, far beyond anything in our current technological roadmap. At 1% of the speed of light, the journey to Proxima Centauri takes 424 years, still more than 4 centuries. More than the time since Galileo first pointed a telescope at Jupiter's moons. More than the entire lifespan of the United States as a nation, several times over. And Proxima Centauri is the closest star. The nearest star with a confirmed planetary system containing planets in the potentially habitable zone of a Sun-like star is significantly farther. Alpha Centauri A and B, the two Sun-like stars in the same triple system as Proxima, are at the same distance as Proxima, 4.37 light-years, and may have planets in their habitable zones, though confirmation remains uncertain. The nearest confirmed habitable zone planet around a Sun-like star that is not part of this system is further still. Most stars visible to the naked eye on a clear night are tens to hundreds of light-years away. At 1% of the speed of light, an achievement that would be extraordinary by any reasonable extrapolation of current technology, traveling to a star 100 light-years away takes 10,000 years. 10,000 years. The entire span of human civilization, from its earliest agricultural settlements to the present, is approximately 10,000 years. A journey to a moderately nearby star would take as long as the entire history of human civilization from beginning to today. This is before we encounter any of the physical problems. This is just the raw geometry of the galaxy, the distances involved, and the maximum speeds achievable with anything approaching foreseeable technology. The result is already staggering. But it gets worse, because traveling at a significant fraction of the speed of light is not just a matter of building a faster engine. It introduces physical problems that have no engineering solution. Let us talk about the interstellar medium. Space is not empty. The interstellar medium, the material filling the space between stars, contains gas and dust at very low densities. Near Earth, in the local interstellar medium, the average density is approximately 1 hydrogen atom per cubic centimetre. This is far less dense than any vacuum achievable in a laboratory on Earth. It seems negligibly thin. At low speeds, it is. At the speeds required for interstellar travel in any reasonable time frame, it is not. At 1% of the speed of light, 3,000 kilometers per second, a spacecraft is moving through the interstellar medium fast enough that hydrogen atoms, which are essentially stationary relative to the spacecraft, hit the spacecraft's leading surface with significant energy. The collision of a single hydrogen atom at 1% of the speed of light is not dangerous. But the flux of hydrogen atoms hitting a spacecraft moving at this speed over years and decades of travel represents a meaningful radiation dose and erosive force on any material facing the direction of travel. The faster the spacecraft moves, the worse this gets. Not linearly. The energy of each individual collision scales with the square of the velocity, double the speed, and each collision delivers 4 times the energy. At 10% of the speed of light, the problem is 100 times worse than at 1%. At 50% of the speed of light, it is 2,500 times worse. At a significant fraction of the speed of light, individual hydrogen atoms, which are individually harmless at everyday speeds, hit the spacecraft with energies comparable to high-energy cosmic rays. A single proton moving at 99% of the speed of light relative to a spacecraft hits with an energy of approximately 6 giga-electron volts, comparable to the particles produced in particle accelerators on Earth, where we go to considerable lengths to contain and shield against them. The cumulative effect of billions of such impacts over a decades-long journey would erode any material we know how to make. The leading face of the spacecraft, Whatever is facing the direction of travel would be hit by a continuous stream of high-energy particles, indistinguishable from a radiation environment more hostile than anything in the solar system outside the Sun's immediate corona. There are proposed solutions: a magnetic shield that deflects charged particles, hydrogen ions, before they reach the spacecraft; a physical shield made of hydrogen ice or beryllium or other materials designed to ablate slowly over the journey, sacrificing themselves to protect the spacecraft behind. The breakthrough Starshot concept for sending small, laser-propelled sails to Alpha Centauri designs its gram-scale probes to be so thin and small that the erosion from interstellar medium impacts is manageable over the several-decade journey. But these solutions come with constraints. Magnetic shields heavy enough to be effective add significant mass to the spacecraft. Physical shields are consumed over the journey and must be replaced or sized to last the entire trip. The breakthrough Starshot approach works for gram-scale probes, but not for anything carrying passengers or significant payload. For a crewed spacecraft, or even a large robotic spacecraft carrying enough equipment to actually do something useful at the destination, the interstellar medium is not a negligible obstacle at relativistic speeds. It is a serious engineering constraint that limits either the speed or the size of the spacecraft, and usually both. Let us now talk about propulsion, about what it actually takes to accelerate a spacecraft to a significant fraction of the speed of light, and why the energy requirements rapidly become incomprehensible. The fundamental relationship is the rocket equation, derived by Konstantin Tsiolkovsky in 1903. It describes the relationship between the final velocity of a rocket, the exhaust velocity of its propellant, and the ratio of initial mass to final mass. The rocket equation has a property that makes high-speed travel deeply problematic. To increase the final velocity significantly, you must increase the mass ratio exponentially. Double the desired final velocity, and the mass ratio does not double, it increases exponentially. For a spacecraft designed to travel at 10% of the speed of light, using the best chemical propulsion available, liquid hydrogen and liquid oxygen, the propellants used in the most efficient chemical rockets, the calculation is straightforward. The exhaust velocity of hydrogen-oxygen combustion is approximately 4.4 kilometers per second. The target velocity is approximately 30,000 kilometers per second. The ratio of target velocity to exhaust velocity is approximately 6,800. The rocket equation tells us that the mass ratio, the ratio of initial mass including propellant to final dry mass, is e to the power of 6,800, where e is the base of natural logarithms, approximately 2.718. E to the power of 6,800 is a number so large that no conventional notation captures it adequately. It is tens of thousands of digits long. For every kilogram of useful payload delivered to 10% of the speed of light, the initial propellant mass required is so vastly larger than the mass of anything that has ever existed in the observable universe that the concept becomes meaningless. The entire mass of the Sun would not provide enough chemical propellant to accelerate a single kilogram to 10% of the speed of light. This is not an engineering problem. It is a mathematical consequence of the rocket equation applied to the physics of chemical combustion. No improvement in chemical rocket design could overcome it. The exhaust velocity of chemical propellants is bounded by the energy available in chemical reactions, and those energies are insufficient by a factor of millions for interstellar travel. Nuclear propulsion helps. Nuclear thermal propulsion, heating propellant with a nuclear reactor, achieves exhaust velocities roughly twice those of chemical rockets. Better, but still insufficient by many orders of magnitude. Nuclear pulse propulsion, using a series of nuclear explosions to propel a spacecraft, achieves higher effective exhaust velocities but still falls vastly short. The most efficient propulsion concept consistent with known physics is the matter-antimatter annihilation drive. When matter and antimatter annihilate, they convert 100% of their mass to energy, the maximum conversion efficiency permitted by E = mc squared. The exhaust from a matter-antimatter engine, if it could be directed efficiently, would have exhaust velocities approaching the speed of light. This would make the mass ratio problem tractable for interstellar travel. But antimatter does not exist in meaningful quantities in nature. It must be produced artificially, particle by particle, in accelerators consuming enormous amounts of electricity. The total amount of antimatter ever produced by human civilization is estimated at approximately 20 nanograms, 20 billionths of a gram, accumulated over decades of operation of the world's most powerful particle accelerators. Annihilating this amount of antimatter with an equal mass of matter would release approximately 1,700 megajoules, equivalent to roughly 400 kilograms of TNT. A matter-antimatter rocket capable of accelerating a crewed spacecraft to 10% of the speed of light would require on the order of thousands of metric tons of antimatter. Producing this quantity of antimatter at any foreseeable rate of production would require millions of years of continuous operation of particle accelerators, consuming more electrical power than all of human civilization currently generates. These are not obstacles that engineering progress will overcome. They follow from the fundamental physics of how much energy chemical and nuclear reactions release, how much energy antimatter annihilation releases, and how much energy is required to accelerate a given mass to a given velocity. The physics is fixed. For an alien civilization to reach Earth from even the nearest star system, assuming they are bound by the same physics we are, they face these same constraints. Their chemistry produces the same energies ours does. Their nuclear reactions release the same energy per nucleon. If they use matter-antimatter annihilation, the production problem is identical in principle. They are not exempt from the rocket equation. Let us now talk about something that changes the calculations somewhat, but does not resolve it. About the effects of special relativity on the experience of interstellar travel, and how time dilation could in principle make very long journeys seem shorter for the traveller. At speeds approaching the speed of light, time dilation becomes significant. A traveller moving at 99% of the speed of light experiences time passing at approximately 1/7 the rate of a stationary observer. At 99.9%, approximately 1/22. At 99.99%, approximately 1/70th. This means that for a traveller on a spacecraft moving at 99.99% of the speed of light, a journey of 4.24 light-years to Proxima Centauri would be experienced as approximately 22 days of personal time. The traveller would age only 22 days. They would subjectively experience a 22-day trip. This seems to resolve the problem. If sufficiently advanced propulsion could accelerate a spacecraft to close enough to the speed of light, travellers could reach even the far side of the galaxy within a human lifetime in terms of personal time elapsed. The galaxy is 100,000 light-years across. At 99.9999% of the speed of light, with time dilation reducing the traveller's elapsed time by a factor of 1,000, a journey across the galaxy would be subjectively experienced as approximately 100 years. Difficult but not impossible for a long-lived crew. But the energy requirements for accelerating to 99.9999% of the speed of light are incomparably larger than for 10% of the speed of light. The Lorentz factor, the time dilation factor, at this velocity is approximately 1,000. The kinetic energy of a 1 kilogram mass moving at this velocity is approximately 1,000 times its rest mass energy, or about 9 times 10 to the power of 19 joules, equivalent to roughly 21 billion tons of TNT for a single kilogram of payload. Accelerating a spacecraft with a few 100,000 kilograms of dry mass, a minimal estimate for any crewed interstellar mission, to 99.9999% of the speed of light would require energy comparable to the total energy output of the Sun over millions of years. The time dilation effect does not reduce the energy required. It merely makes the journey subjectively shorter for the crew. The energy problem remains. The interstellar medium problem remains, and at these velocities it becomes catastrophically worse, with each hydrogen atom hitting the spacecraft with the energy of a cosmic ray particle. The time dilation solution to interstellar travel is real in a physical sense. It is a genuine consequence of special relativity, but it does not make the journey possible in any practical sense, because the energy requirements for achieving the velocities required are beyond any plausible technological capability. Let us now talk about a class of problem that is even more fundamental than energy, about what the universe's own expansion does to the problem of intergalactic travel, and why certain things are impossible not merely in practice, but in principle. We have discussed the difficulty of interstellar travel between stars within a galaxy, but the observable universe contains approximately 2 trillion galaxies. If any intelligent species exists in another galaxy and wants to reach Earth, or if we ever wanted to reach another galaxy, what does the physics say? The answer depends on which galaxy. The Andromeda galaxy, the nearest large galaxy to the Milky Way, is approximately 2.537 million light-years away. At any velocity less than the speed of light, reaching Andromeda would take more than 2.537 million years of travel time, as measured by external observers. Even with extreme time dilation, the energy required would be incomprehensibly large. But here is the thing that goes beyond mere difficulty into principle. The universe is expanding. The space between galaxies is not fixed. It is growing, driven by dark energy, and that growth is accelerating. Galaxies beyond a certain distance, the Hubble radius, approximately 14 billion light-years, are currently receding from us at velocities exceeding the speed of light due to this expansion. This is not a violation of special relativity. Objects are not moving through space faster than light. Space itself is expanding, and the cumulative expansion of enough space adds up to a recession velocity greater than light. The distinction matters because special relativity's limit on the speed of light as a speed through space does not prevent space itself from expanding at any rate. The practical consequence is a cosmic event horizon. Beyond approximately 16 billion light-years, the event horizon for our location in an accelerating universe, objects are receding from us so fast that any signal or object we send toward them today can never reach them, even traveling at the speed of light. The expansion is fast enough and accelerating enough that the gap between us and objects beyond the event horizon grows faster than we can close it. Any civilization in a galaxy beyond our cosmic event horizon can never reach us. Not because the journey is too long, because the structure of space-time makes it impossible. Light emitted now from beyond the event horizon will never arrive at Earth. A spacecraft launched from beyond the event horizon will never arrive at Earth. No physical process can bridge that gap. This is the first truly hard impossibility. Not an engineering challenge, but a physical one built into the large-scale structure of the universe. Most of the observable universe is beyond this event horizon. We can see objects up to approximately 46 billion light-years away, the radius of the observable universe, because their light was emitted in the past when they were closer to us, before the universe had expanded as much. But the objects themselves are now beyond our event horizon. Any civilization in those galaxies we observe today is permanently, physically unreachable, and we are permanently, physically unreachable from them. Let us now talk about what might seem like a way around all of these problems, about the various hypothetical mechanisms for faster-than-light travel that appear in physics literature and science fiction, and what physics actually says about each. The most common proposal is the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper showing that Einstein's general relativity, which describes space-time as a dynamic entity that can curve and warp, admits solutions in which a region of space-time contracts in front of a spacecraft and expands behind it. Within this warped bubble, the spacecraft is locally at rest, but the bubble itself and the spacecraft inside it moves at effectively faster than light speeds relative to distant observers because the spacecraft is riding a wave of space-time curvature rather than moving through space. This is a real solution to Einstein's equations. The mathematics is genuine. The physics, as far as we can tell, does not forbid a space-time geometry with these properties. But there are problems, severe ones. The most immediately practical problem is that maintaining an Alcubierre warp bubble requires negative energy density, exotic matter with negative mass, in large quantities. Negative energy density exists in quantum mechanics in small amounts and under specific conditions associated with the Casimir effect. But the amounts required to maintain an Alcubierre bubble of any practical size, even a bubble just barely large enough to enclose a spacecraft, are calculated to exceed the total positive energy of the observable universe by many orders of magnitude. Subsequent refinements to the original Alcubierre proposal have reduced the exotic matter requirement substantially. Harold White at NASA worked on modifications that reduced the required exotic matter to more manageable but still extraordinary quantities. But even the most optimistic estimates require exotic matter in amounts that vastly exceed anything we have observed or could plausibly produce. There is also the problem of control. An Alcubierre bubble, once formed and in transit, is causally disconnected from the outside universe in a specific way. The interior of the bubble cannot send signals forward to the region of warped space-time ahead of it. This means that from inside the bubble you cannot steer. You cannot send signals to slow down or stop. The spacecraft is, in a meaningful sense, trapped inside the bubble, unable to control its own trajectory once the bubble is in motion. There are also problems related to Hawking radiation and quantum vacuum effects within the bubble that suggest it may be intrinsically unstable. And there is a deep problem related to causality. If faster-than-light travel is physically possible, it becomes possible, in principle, with the right reference frame, to also travel backward in time. The same physics that allows FTL travel in one direction allows causal loops in which an event causes its own past. The grandfather paradox is not just a philosophical puzzle, it represents a genuine logical inconsistency that most physicists take as evidence that whatever theory of quantum gravity eventually supersedes general relativity, it will not permit FTL travel. Wormholes, the other commonly discussed FTL mechanism, have similar problems. Traversable wormholes require exotic matter to remain open. The energy conditions violated by traversable wormholes are the same ones that permit Alcubierre drives. The causality problems are the same. Wormholes are consistent with general relativity as mathematical solutions, but their physical realizability is deeply questionable. The current consensus in theoretical physics is that both wormholes and warp drives, while consistent with general relativity in principle, require physics we do not have, specifically exotic matter in quantities that appear physically unrealizable, and that whatever theory of quantum gravity eventually unifies general relativity with quantum mechanics will likely eliminate these solutions as physically accessible. This does not prove FTL travel is impossible. It is a stronger statement than that. It says that within our current best physical theories, FTL travel requires exotic matter in unrealizable quantities, produces causality paradoxes, and has no known physically realizable mechanism. For a civilization constrained by the same laws of physics we are, and we have no reason to believe the laws of physics are different elsewhere in the universe, this represents a hard barrier. Let us now talk about something that is not speculative but directly measurable, about the evidence from our own searches for visiting alien spacecraft, and what those results actually tell us. For over 60 years, humanity has been conducting systematic searches for signals from extraterrestrial intelligence. Radio telescopes have surveyed millions of stellar systems for artificial electromagnetic signals. The result is 0 confirmed detections. Additionally, various searches have looked for physical evidence of alien visitors. NASA tracks objects in near-Earth space with sufficient precision to detect spacecraft of any reasonable size. The solar system has been surveyed by our own spacecraft. We have detailed maps of the inner solar system. We have visited every planet. We have sent probes to the outer solar system. No artifacts of non-human origin have been confirmed. The asteroid Oumuamua, detected in 2017 as the first confirmed interstellar object to pass through the solar system, generated significant scientific discussion about whether it might be an artificial object, partly because of its unusually elongated shape and its non-gravitational acceleration. Subsequent analysis has produced conventional explanations, most likely a fragment of a nitrogen ice sheet from a Pluto-like object disrupted by a past stellar encounter, or possibly a hydrogen iceberg. The scientific consensus does not support an artificial origin. The absence of confirmed alien visitors is consistent with the physics we have been discussing. If interstellar travel is either impossible at meaningful timescales or requires energy expenditures that no civilization can sustain, then the absence of visitors is expected, not because other civilizations don't exist, but because the physics makes visiting effectively or actually impossible. Let us now talk about something deeper, about what the combination of these physical constraints means for our picture of the universe and intelligent life within it. The universe contains approximately 2 trillion galaxies. Our galaxy alone contains several hundred billion stars. The fraction of stars with planets is now known to be close to 1. Essentially, every star has planets. The fraction of those with planets in the habitable zone is smaller but still substantial. By any reasonable extrapolation, the universe should contain staggering numbers of planets capable of supporting life. And yet the night sky is silent. No confirmed signals, no confirmed visitors, no confirmed evidence of any other civilization anywhere in the observable universe. This is the Fermi paradox stated in its most fundamental form. The universe appears to have the conditions for life everywhere, and yet we see no evidence of life anywhere other than Earth. The physical impossibility of interstellar travel, or its practical impossibility on any timescale shorter than tens of thousands to millions of years, is one possible partial resolution. If civilizations cannot travel between star systems at any meaningful rate, then even a universe full of civilizations would be one in which each civilization is effectively isolated from all others. The silence would be expected. But this resolution only applies to physical presence, to visitors. It does not explain the silence in electromagnetic signals, which travel at the speed of light and do not face the energy or interstellar medium problems that physical travel does. A civilization 100 light-years away that began transmitting powerful radio signals 100 years ago would be detectable with current Earth technology, if they were transmitting in the right frequency range with sufficient power. The absence of detectable signals from any direction is a separate puzzle from the absence of physical visitors. The impossibility of travel does not explain the electromagnetic silence. Let us now talk about the specific problem of targeting, about what a civilization attempting to send a spacecraft to Earth would actually need to know, and how the moving nature of the solar system makes even specifying the destination an extraordinary challenge. Earth is not sitting still. The Earth moves around the Sun at approximately 29.8 kilometers per second. The Sun moves around the center of the Milky Way at approximately 220 kilometers per second. The Milky Way moves relative to the cosmic microwave background reference frame at approximately 600 kilometers per second. A spacecraft launched from Alpha Centauri today with the goal of reaching Earth would need to be aimed not at where Earth currently is, but at where Earth will be when the spacecraft arrives. At even 1% of the speed of light, the journey to the nearest star takes 424 years. Where will the Earth be in 424 years? It will have completed approximately 424 orbits of the Sun. Its position at the end of those 424 years is predictable in principle. Orbital mechanics allows calculation of its future position with high precision. But the precision required is extreme. The Earth has a radius of approximately 6,371 kilometers. To hit a target the size of Earth after a journey of 40 trillion kilometers requires precision in the launch direction of better than 1 part in 6 billion. The slightest error in initial trajectory, in the angle of launch, in the timing, in the exact velocity, compounds over the 424-year journey to produce a miss that could be larger than the solar system. During the 424-year transit, the spacecraft would need to navigate with essentially no external correction capability. Any radio signal sent from the destination to correct its course would arrive 4.24 years after being sent, and any response from the spacecraft would take another 4.24 years to arrive. The correction cycle is 8+ years for each round-trip communication. This does not make interstellar navigation impossible. In principle, it is solvable, but it adds another layer of difficulty to the already extreme engineering challenge. Let us now talk about what all of these considerations, combined, actually mean for the question of whether aliens could ever reach Earth. The honest answer is nuanced in a way that rarely gets stated. Some things are physically impossible by the best understanding we have of the laws of nature. Faster than light travel, whether via warp drives, wormholes, or any other mechanism consistent with known physics, requires either physics that does not exist in our universe or exotic matter in quantities that cannot be realized. Any civilization attempting it faces the same barriers we do. If physics works the same everywhere, and we have every reason to believe it does, since the same atomic spectra, the same gravitational constants, the same speed of light appear throughout the observable universe, then FTL travel is not something that civilizations simply develop with sufficient time and technology. It may be impossible for anyone. Some things are practically impossible on any timescale relevant to biological life. Even at significant fractions of the speed of light, a technological achievement far beyond anything on our roadmap, journeys between stars take centuries to millennia in ship time and much longer in external time. The energy required is orders of magnitude beyond any foreseeable capability. The interstellar medium erosion problem requires significant engineering solutions that constrain speed or mass or both. Some things become absolutely impossible due to the universe's own expansion. Any civilization in a galaxy beyond our cosmic event horizon cannot reach us, regardless of their technology. The expansion of space-time itself makes the journey impossible. Not difficult, impossible. And some things are possible in principle, but so difficult that they constrain what we should expect. A civilization might, over millions of years with extraordinary resources, develop generation ships capable of traveling at a few % of the speed of light and reaching neighboring star systems over centuries. This is conceivable within known physics. It does not require FTL travel or exotic matter or energy sources beyond the total output of a star. But such travel would be extraordinarily rare and extraordinarily slow. A civilization that colonized neighboring star systems at 1/10 of 1% of the speed of light would take 4,000 years per star system hop. Spreading across the galaxy at this pace, if they started at the galaxy's edge, would take hundreds of millions of years. It is possible in principle. It is consistent with the absence of alien visitors, because if it takes hundreds of millions of years to spread across the galaxy and civilizations have finite lifetimes, the intersection of any particular civilization's expansion radius with any particular star system is small. This is the honest picture. Not that aliens definitely cannot reach Earth, but that the physics between the energy requirements, the interstellar medium, the time dilations, the cosmic event horizon, and the navigational precision required makes it either physically impossible or so demanding that it should be extraordinarily rare. The night sky is not silent because no one is out there. The night sky may be silent because the universe is structured in ways that make the distances between inhabited worlds effectively, and in some cases absolutely, uncrossable. Let us now go deeper into the specific numbers, into what the energy requirements actually mean in terms of comparison to things we can measure. The kinetic energy of a 1,000 kilogram spacecraft, roughly the mass of a small car, far less than any crewed vessel, traveling at 10% of the speed of light, is approximately 4.5 times 10 to the 17th power joules. For comparison, the total energy consumption of all of human civilization in a year is approximately 5.8 times 10 to the 20th power joules. So the kinetic energy of a 1,000 kilogram spacecraft at 10% of the speed of light is roughly equal to about 1,000th of humanity's annual energy budget. This seems manageable until you consider that the propellant required to accelerate the spacecraft carries far more mass than the spacecraft itself. With even the most efficient conceivable propulsion, matter-antimatter annihilation, the mass ratio for achieving 10% of light speed is approximately 1.2. That means for every kilogram of final spacecraft mass, you need about 0.2 kilograms of fuel. This is relatively benign, but decelerating at the destination requires another mass ratio of 1.2, and if you want to return, another acceleration and deceleration. The compounding of mass ratios means that a round-trip mission at 10% of the speed of light using perfect matter-antimatter propulsion requires approximately 2.1 kilograms of antimatter for every kilogram of final payload. For a crewed spacecraft, which needs life support, food, water, radiation shielding, scientific equipment, and a return vehicle, the final payload mass might be on the order of 100,000 kilograms. This requires approximately 210,000 kilograms of antimatter. The total antimatter produced by human civilization to date is approximately 20 nanograms, 20 billionths of a gram. We would need to produce 210,000 kilograms, a factor of about 10 to the power of 19 more antimatter than we have ever produced. If antimatter production could somehow be scaled up by a factor of 1 billion immediately, we would still need 10 billion years, longer than the age of Earth, to produce enough. This is why antimatter rocket interstellar travel, while physically possible in principle, is practically impossible with any conceivable rate of antimatter production. Let us now talk about the proposals that have been actually seriously studied, the ones that try to work within these constraints rather than hoping for FTL breakthroughs. The most technically detailed and seriously funded interstellar mission concept is Breakthrough Starshot. Proposed by Yuri Milner and supported by Stephen Hawking among others, Starshot proposes to send a fleet of gram-scale probes, thin sails, perhaps a few meters across with electronics attached, to Alpha Centauri by accelerating them with a powerful ground-based laser. The laser pushes the sail for a few minutes after launch, accelerating it to approximately 20% of the speed of light. At this velocity, the journey to Alpha Centauri would take approximately 20 years. The probes would fly past the system. They cannot decelerate because there is no laser at Alpha Centauri to slow them down, and transmit data back during their brief encounter. The concept is technically serious. The individual components, high-powered lasers, thin film sails, miniaturized electronics, are extensions of existing technology rather than requiring completely unknown physics. The power requirement for the laser array is approximately 100 gigawatts, roughly equivalent to the total electrical generating capacity of the United Kingdom. This is large, but not beyond the scale of existing civilization-level energy production. The sails must be extraordinarily thin, essentially atomically thin in some conceptualizations, to keep the mass low enough to reach the required velocity with the available laser power. The electronics must survive 20 years in the interstellar medium at 20% of the speed of light, where each interstellar dust grain impact releases energy equivalent to a high explosive detonation relative to the sail's mass. These are genuine engineering challenges without existing solutions, but they are not in principle impossible. Breakthrough starshot represents a concept that might be achievable with a few decades of focused technological development and tens of billions of dollars of investment. What Starshot cannot do is send anything capable of interacting meaningfully with another civilization. Gram-scale probes cannot carry instrumentation capable of detecting life, communicating with an alien civilization, or doing anything other than taking low-resolution photographs and transmitting them over a 20-year communications lag. Crewed Starshot is not feasible because the mass of a crewed spacecraft is orders of magnitude larger than the gram-scale probes the laser can accelerate to 20% of light speed. Scaling the laser to push a crewed spacecraft to comparable velocities would require a laser array with power output comparable to the entire global energy consumption of civilization. So Starshot represents the most realistic, currently conceivable interstellar mission concept. And what it can do is send a camera and a few sensors at 1/5 the speed of light to take photos during a flyby and transmit them back over 2 decades. This is the current state of interstellar travel technology, extrapolated forward by several decades. For context, this is what it would take for us to send something, not someone, something, to the nearest star. Any alien civilization trying to send a physical visitor to Earth faces constraints at least this severe. Let us now talk about the communication alternative, about whether the impossibility or near impossibility of physical travel means that any contact with alien civilizations would have to be through signals rather than visitors, and what the physics of signal travel implies. Radio waves, light, and all other forms of electromagnetic radiation travel at the speed of light, approximately 300,000 kilometers per second. This is vastly faster than any spacecraft we can conceive of building. A signal from a civilization 100 light-years away reaches us in 100 years, rather than the tens of thousands of years a physical visit would require. But the speed of light is also a limit on signal travel. A signal sent from 100 light-years away takes 100 years to arrive. Any conversation has a round-trip delay of 200 years. A civilization that tried to have a real-time conversation with Earth from 100 light-years away would ask a question and receive an answer 200 years later, by which time the person who answered would have been dead for generations. At galactic scales, the communication delay becomes extreme. A signal from the far side of the Milky Way, 100,000 light-years away, takes 100,000 years to arrive. Any response takes another 100,000 years. A conversation lasting several exchanges would span hundreds of thousands of years. And for galaxies beyond our cosmic event horizon, roughly 16 billion light-years away, even signals cannot arrive. The expansion of space-time between us and those galaxies is fast enough that light emitted now from beyond the horizon will never reach us. No signal, no spacecraft, no information of any kind can cross the event horizon in either direction. The universe's own expansion imposes an absolute limit on not just physical contact, but any form of contact, including electromagnetic signals, with the majority of the universe. The observable universe, which we can see because light from those regions was emitted in the past when the universe was smaller and those regions were within the light travel distance, is not the reachable universe. Most of what we can see is beyond our event horizon. We observe their past, but can never interact with their present. This is the physical reality of contact between civilizations in an accelerating, expanding universe. What we can potentially reach via signals are civilizations within our cosmic event horizon of approximately 16 billion light-years, with communication delays measured in years, thousands of years, millions of years, or billions of years, depending on distance. Physical contact via spacecraft is limited to perhaps the nearest few thousand light years, and even that requires technology far beyond our current capability and timescales, measured in tens of thousands of years at realistic velocities. These constraints apply equally to any civilization elsewhere in the universe. Let us talk about something that takes all of these physical constraints and makes them personal, about what it actually means to live in a universe where the distances between inhabited worlds are effectively uncrossable, and what this implies about the nature of intelligent life throughout the cosmos. There is a version of this discussion that ends with despair. The universe is incomprehensibly large. The distances between stars are so vast that physical contact is effectively impossible. The laws of physics conspire to isolate every inhabited world from every other. We are alone in a practical sense, even if we are not alone in an absolute sense. This version is accurate but incomplete. There is another version that sees the same facts differently. Every intelligent civilization that has ever existed in the universe, every species that developed curiosity and science and the ability to look up and wonder what is out there, has confronted the same night sky, has seen the same stars, has discovered the same speed of light and the same rocket equation, and the same inverse square law and the same expansion of space-time, has arrived at the same conclusion. The distances are real, the constraints are real, the isolation is real. And yet, and this is the thing that changes the meaning of the isolation, every one of those civilizations could, in principle, send a signal. Not a visitor. A signal. Electromagnetic radiation traveling at the speed of light, constrained by the same limits as everything else, but faster than any physical object. Capable of crossing the distances between stars in years rather than millennia. The universe permits communication on timescales that are long, but not infinitely long. A civilization 1,000 light-years away could send a signal. It would take 1,000 years to arrive. The round trip would take 2,000 years. But both are finite. Both are numbers, not infinities. This means that the isolation imposed by the physics of travel is not the same as total isolation. It is the isolation of extreme distance and extreme time, of gaps between exchanges that span human lifetimes and generations, but not the absolute isolation of a universe in which no information could cross the gaps at all. We are not in contact with any other civilization. We have found no signals. We do not know whether any other civilization exists within signal range. But the physics permits the possibility of signal contact in a way that it does not permit the possibility of physical visits, except over timescales that strain the meaning of the word. Let us now talk about something that is often glossed over in discussions of alien contact, about what the actual requirements are for detecting and recognizing an artificial signal, and why this is a non-trivial problem, even if signals are being sent. Detecting a signal requires that the signal be powerful enough to still be detectable after traveling the relevant distance, transmitted in a frequency range we are monitoring, transmitted in a direction we are looking, transmitted in a way that allows us to distinguish it from natural astrophysical sources, and transmitted at a time when we happen to be looking. Each of these requirements narrows the probability of detection independently. Together, they mean that even if 1,000 civilizations within signal range were actively transmitting, we could miss all of them if any of the above conditions were not met. The inverse square law is brutal. The power of an electromagnetic signal decreases as the square of the distance. A transmitter at 100 light-years produces a signal at Earth that is 100 times weaker than the same transmitter at 10 light-years. At 1,000 light-years, 10,000 times weaker. At 10,000 light-years, 1 million times weaker. The most powerful radio transmitter ever built on Earth, the Arecibo planetary radar, transmits at approximately 1 megawatt when used as a radar. At 1,000 light-years, this signal would be essentially undetectable with current radio telescope technology. We would need to be looking specifically in the right direction with our most sensitive instruments to have any chance. A civilization attempting to signal us would need either to be much closer, to use much more power, to aim their signal specifically at us, or some combination of all three. Aiming specifically at us requires knowing we are here. For a civilization more than a few hundred light years away, even knowing that Earth has an inhabited planet is not guaranteed. The signs of Earth's technological civilization, radio emissions, atmospheric modification, only extend a few hundred light years at most and would be weak even at that distance. Transmitting with much more power, say 1,000,000 times more than our best transmitters, would extend the range significantly, but requires building transmitters more powerful than anything we have constructed. A civilization could achieve this with a sufficiently large power source. A stellar-scale transmitter powered by a Dyson sphere, for example, could transmit at levels detectable across the galaxy. But we would expect to see evidence of such a civilization's energy use in astronomical surveys, and searches for Dyson spheres and other technosignatures have found no confirmed examples. The absence of detected signals after 65 years of searching is meaningful but not conclusive. We have searched a tiny fraction of the possible parameter space, a small number of stars, a limited range of frequencies, a limited range of signal types, for a limited period of time with limited sensitivity. The absence of a signal in what we have searched does not strongly constrain whether signals exist, but it does constrain the number of civilizations transmitting powerful, wide-spectrum, omnidirectional signals toward Earth specifically. The number appears to be zero or very small. Let us now talk about a concept that changes how we think about the problem. About the difference between civilizations that choose to transmit and civilizations that do not, and why the silence we observe might be explained by this distinction rather than by the absence of civilizations. The logic of signaling across interstellar distances is strange from the perspective of any individual civilization. If you transmit a signal today, you will not receive a response for, at minimum, twice the distance to the nearest civilization, in light years. If the nearest civilization is 1,000 light years away, you transmit today, and they receive it in 1,000 years, and respond immediately. You receive their response in 2,000 years. Not you personally, not your civilization as it exists today. Whatever your civilization becomes in 2,000 years, if it still exists. This is a communication system with round-trip delays measured in millennia. Any conversation is not between two parties. It is between versions of those parties separated by thousands of years of change, development, and possible extinction. This makes the signaling game extremely strange. Transmitting requires dedicating resources to a communication system that will not produce results within any individual's lifetime, or probably within many generations of individuals. The benefits, if any, accrue to future versions of your civilization that may be completely different from the civilization that transmitted. This is not impossible. Humanity builds cathedrals that take generations to complete. We plant trees whose shade we will never sit in. We pursue scientific programs whose results we will not live to see. Long-term investment is part of human civilization, but it is expensive, and the probability of success is unknown. And the content of any response, received 2,000 years from now, cannot be anticipated. If most civilizations make the rational calculation that signaling is too expensive and too uncertain to justify, that the resources required for a powerful transmitter are better spent on more immediate needs, then the universe would be full of civilizations, none of which were actively transmitting. The electromagnetic silence would persist, not because no one is there, but because no one has chosen to speak. This is the hypothesis sometimes called the quiet universe, or the radio silence hypothesis. It does not require that civilizations destroy themselves. It does not require that life is rare. It requires only that active, sustained, powerful electromagnetic signaling directed toward unknown destinations is not a priority for most civilizations. This hypothesis is uncomfortable because it is consistent with all of our observations and yet provides no testable prediction beyond the prediction we are already living: silence. Let us now talk about something that is more specific and more grounded, about what the physical impossibility of alien visits tells us about specific claims of alien visitation that have circulated in popular culture and more recently in government disclosures. The United States government has declassified and released information about unidentified aerial phenomena, UAP, that its military has observed. This information has generated significant public discussion about whether some UAP might represent technology of extraterrestrial origin. The physics we have been discussing provides context for evaluating these claims. If alien visitors are genuinely present in Earth's atmosphere, they have either achieved faster-than-light travel, overcoming the barriers we discussed, including the requirement for exotic matter in quantities approaching the total energy content of the universe, or they have undertaken a journey of thousands to millions of years in conventional speed spacecraft. The FTL option requires physics that does not exist in our best understanding of nature and may not exist at all. The slow travel option requires that a civilization decided to send a spacecraft to Earth specifically, launched it thousands of years ago or longer. It arrived at Earth, and rather than making unambiguous contact, which would have required only sending a signal we could not mistake for natural phenomena, it began conducting surveillance that is only detectable as anomalous aircraft behavior seen by military pilots. Both scenarios strain credulity in ways that go beyond simple skepticism. The first requires overturning the most well-tested physical theories in history. The second raises the question of why a civilization capable of crossing interstellar space would choose to behave in a way indistinguishable from malfunctioning Earth technology, rather than announcing their presence unambiguously. The most parsimonious explanation for UAP observations, given what physics tells us about the difficulty of interstellar travel, remains that they are misidentified Earth phenomena. Not all of them are explained, and unexplained observations deserve continued investigation. But the prior probability that any given unexplained observation represents an interstellar visitor, given the physical barriers to such a visit, is very low. This is not a dismissal of the observations. It is a statement about priors. The observations are real. The people reporting them are credible. What those observations represent requires evaluation against a background that includes how difficult it is to get here from anywhere else. Let us now talk about the long-term future, about what the physical constraints on interstellar travel mean for the fate of intelligent life in the universe over cosmological timescales. The universe is approximately 13.8 billion years old. The Sun will become a red giant in approximately 5 billion years, making Earth uninhabitable. Other stars will continue burning for trillions of years. The universe will be capable of supporting stars and habitable planets for at least 100 trillion years from now, roughly 7,000 times the current age of the universe. Over this time frame, any civilization that survives long enough has potential access, at least in principle, to the galaxy. Even at velocities of only 0.1% of the speed of light, a civilization could spread across the entire galaxy in approximately 100 million years. This is a long time by human standards, but a tiny fraction of the time available before the last stars burn out. If any civilization in the galaxy has existed for even a few 100 million years and has maintained continuous technological capability and has chosen to spread, it could have reached Earth long ago. The absence of such visitors, the fact that Earth shows no clear signs of having been colonized or even visited by an extraterrestrial civilization, is one of the most striking aspects of the Fermi paradox applied at long timescales. The physical barriers we have discussed do not fully resolve this. They slow expansion, certainly. They impose enormous energy costs. They require extraordinary engineering. But they do not make galaxy-wide spread impossible over hundreds of millions of years. Something else must account for the absence. Either civilizations are rare enough that none have reached us yet, which requires specific values in the Drake equation, or civilizations that exist do not spread, which requires a consistent behavioral pattern across all civilizations. Or civilizations do not last long enough, which requires some form of the Great Filter. Or we are the first, which requires that we are at an extremely early moment in the universe's history of developing intelligence. The physics of interstellar travel makes each hop between star systems slow and costly. It does not make the galaxy uncrossable over civilizational timescales. So while the physics provides a partial explanation for why we have not been visited, making quick visits nearly impossible and even slow multi-generational ones extraordinarily expensive, it does not provide a complete explanation for why no civilization anywhere in the galaxy appears to have spread to the point of reaching Earth over billions of years of cosmic time. This is the deeper version of the Fermi paradox, and it remains unresolved. Let us now talk about what all of this means for how we should think about our own future, about whether humanity has any realistic path to becoming an interstellar species, and what the physical constraints imply for the long-term trajectory of human civilization. The physical constraints are real and severe, but they are not perfectly uniform across all options. The nearest stars are within range of generation ships, spacecraft that travel for centuries or millennia at speeds achievable with extensions of current technology. A spacecraft traveling at 0.1% of the speed of light reaches Proxima Centauri in approximately 4,000 years. This is long, but it is finite. It is a number, not an infinity. A civilization that genuinely committed to interstellar colonization could send generation ships to neighboring stars, accept the thousands of years required for each hop, and over tens of thousands of years establish a presence in the nearest dozen or so star systems. The energy barrier, while severe, is not absolute at low velocities. A spacecraft traveling at 0.1% of the speed of light does not require matter-antimatter fuel. Plausible extensions of nuclear propulsion, nuclear pulse propulsion, nuclear fusion propulsion could in principle achieve these velocities with mass ratios manageable enough to be physically conceivable, if not currently achievable. The interstellar medium at 0.1% of the speed of light is not the catastrophic erosion problem it is at 10% or higher. The collision energies are much lower. Physical shielding is more feasible. The problem is manageable rather than fundamental. So the physically possible scenario for human interstellar expansion is very slow, requiring generations or millennia per star system, requiring extraordinary commitment of resources over timescales much longer than any current institution or civilization has sustained, requiring motivations that remain stable across thousands of years of social and technological change, and reaching only the nearest few dozen star systems over tens of thousands of years. This is a far cry from the galaxy-spanning civilizations of science fiction. But it is not zero. It is a path, albeit an extraordinarily difficult one, from here to there, from a single planet species to a multi-stellar presence, that does not require overturning fundamental physics. Whether humanity or any successor civilization will actually walk that path is unknown. Whether the motivation, the institutional continuity, the resources, and the survival to make that commitment possible will materialize is genuinely uncertain. But the physics permits it, barely, slowly, at enormous cost, over timescales that make the entirety of recorded human history look like a brief introduction. Let us now talk about what this means experientially, about how it feels and how it should feel to understand these constraints. Most discussions of interstellar travel focus on the technology. What engines could we build? What materials could we use? How could we generate enough power? These are real and important questions, but there is another dimension that is rarely discussed. What does it mean to be a civilization that understands these constraints, that knows the distances, knows the rocket equation, knows the speed of light, and must decide how to relate to the universe given what that knowledge implies? We are a species that has been on Earth for approximately 300,000 years. We have had agriculture for approximately 10,000 years. We have had telescopes for approximately 400 years. We have had radio for approximately 130 years. We have had rockets capable of reaching space for approximately 70 years. In that 70 years, we have sent probes to every planet in the solar system. We have placed humans on the moon. We have launched spacecraft that have left the heliosphere and entered interstellar space. The pace of our expansion into space is genuinely extraordinary by the standards of any previous expansion in human history. And yet, our fastest spacecraft would take 73,000 years to reach the nearest star. The nearest star. At the absolute limit of what we have achieved in 70 years of spaceflight, the gap between what we have accomplished and what interstellar travel requires is not a gap that closes steadily over time. It is not like the gap between early aviation and modern aviation, where each decade brought genuine doubling of speed or halving of cost. It is a gap that requires not incremental improvement, but fundamental change, either in propulsion physics, in our relationship to time and generational continuity, or in what we are willing to commit over centuries. That fundamental change is not impossible. History has surprises. Physics has not yet reached its end. Technologies sometimes emerge that change the calculus entirely. But operating on the current state of knowledge, in the current physical universe as we understand it, the honest reckoning is this. The stars are not far away in the way that London is far from New York. Far in the sense that getting there is expensive and time-consuming, but obviously achievable. They are far in a way that challenges what it means to be a civilization that wants to reach them. They are separated from us by distances that, at any speed we know how to achieve, imply journey times measured in the lifetimes of nations. And any alien civilization that wanted to reach us faces the same mathematics. The universe is not an empty space waiting to be explored. It is a structured physical reality with specific properties, a specific speed of light, a specific rocket equation, a specific amount of energy available from specific reactions. And those properties make the distances between inhabited worlds into something qualitatively different from distances on Earth. Not just large, immense in a way that reshapes what is possible, for us, for anyone. Let us talk about something that requires sitting with discomfort, about the specific emotional and intellectual experience of understanding these constraints fully, and why that experience is different from simply knowing that space is big. Most people have heard that space is big. They have heard the distances. They have heard the light years. They process this information and return to their lives relatively unchanged, because the numbers are too large to feel. 4.24 light years, 40 trillion kilometers. These are not visceral. They do not produce in the listener the same physical response as a height or a cold or a pain. But there is a different way to encounter these constraints that does produce a visceral response, and it comes from following the logic all the way to its conclusion, rather than stopping at the number. Follow it this way. Every star you can see tonight is a sun. Most of them have planets. A significant fraction of those planets are in the right temperature range for liquid water. Some fraction of those are rocky. Some fraction of those have atmospheres. Some fraction of those have had billions of years to develop complex chemistry. And yet the fastest thing we have ever built would take 73,000 years to reach the nearest one. Not 73,000 years to reach all of them, 73,000 years to reach the nearest one, the one 4 light years away, the dot of light most immediately above the horizon. 73,000 years is approximately the time since anatomically modern humans first left Africa. It is the entire span of human prehistory, from the earliest migrations to the invention of writing and cities and civilization, and then all of recorded history on top of that, repeated approximately 8 times. And that is to reach the nearest star. The rest are further. Some are tens of light years, hundreds, thousands. The galaxy is 100,000 light years across. At any speed we can conceive of building with foreseeable technology, the galaxy is not a place we can travel. It is a place we can look at. It is a place we can measure and categorize and understand in extraordinary detail from this one fixed point. But travel to it, in any meaningful sense of travel involving human lifetimes or even human institutional continuity, is not available to us. The same constraint applies to anyone else. Any civilization within the galaxy faces the same basic physics, the same distances, the same energy requirements, the same rocket equation applied to the same fundamental forces. And here is where the visceral part comes in. If you follow the logic fully, you arrive at this. There may be hundreds, or thousands, or millions of civilizations scattered throughout the Milky Way, each looking out at the same galaxy, each discovering the same constraints, each understanding that the distances are real and the physics is not negotiable, each arriving at the same quiet conclusion that the stars visible in their own sky, however many there are, however bright, however obviously host to planets, are not reachable in any timescale that feels human. And each of those civilizations, like us, sitting with the knowledge that they are probably not alone, and simultaneously that the distances mean they will probably never know for certain. This is the specific existential content of the Fermi paradox understood at the physical level. Not the puzzle of where everyone is, the reality of what it means to exist in a universe structured this way, where the distances between places where minds might exist are so vast that those minds cannot reach each other and may not be able to signal each other effectively, and will each independently arrive at the discovery that they are most likely not the only ones, while simultaneously being unable to confirm it. Sitting with that fully, not processing it and moving on, but actually sitting with it, produces something that is neither hope nor despair, but something more complex, a kind of recognition of the specific shape of our situation, an acknowledgement that the universe does not owe us the comfort of contact, that being intelligent in this universe means being isolated in ways that intelligence itself cannot overcome. This is not a small thing to understand. Let us now talk about something that complicates the picture in an important way, about the fact that the constraints on travel are not the same as constraints on influence, and what this means for thinking about interstellar civilizations. A civilization cannot send a spacecraft to Earth in any reasonable time, but a civilization can send information. Not in real time, the speed of light delay is real and unavoidable, but over centuries or millennia, information can cross interstellar distances in ways that physical objects cannot. What kind of information? Science, obviously. The laws of physics are the same throughout the observable universe. A civilization that has discovered quantum mechanics and general relativity and thermodynamics has discovered the same things we have discovered. The content of their physics textbooks would be recognizable to ours. Not in language or notation, but in content. If they transmitted their scientific knowledge and we received it, we would understand it. But also culture, art, history, philosophy, values, ways of organizing society. The accumulated experience of a civilization that has perhaps solved problems we have not yet faced. Population management, resource limitation, existential risk, the governance of advanced technology. A civilization that survived the transition to advanced AI, for example, a transition we are beginning now, and which may be the most dangerous transition any technological civilization faces, would have knowledge of how to do that. If they chose to transmit that knowledge, and if it reached us in time, it could be the most valuable information ever received by human civilization. The impossibility of physical travel does not eliminate the possibility of this kind of influence. It just slows it to light-speed timescales, which for nearby civilizations, within a few hundred light years, means centuries of delay. Not forever. This is why the search for signals matters even given the impossibility of physical visits. The absence of alien visitors does not mean the absence of alien transmissions. The two are controlled by completely different physics. Visitors require energy and mass transport across light years. Signals require only photons, massless, travelling at the maximum possible speed, costing vastly less energy than any physical spacecraft. If any civilization within signal range is transmitting, and we are listening with sufficient sensitivity in the right frequency ranges at the right times, we could receive information that has travelled for centuries or millennia across the galaxy. Information that is old by the time it arrives, but potentially no less valuable for being old. Science does not expire. Mathematical proofs discovered 10,000 years ago are still valid. The content of interstellar transmission, whatever it is, would remain true regardless of how long it took to arrive. This asymmetry between the near impossibility of physical contact and the physical possibility of signal contact is important for how we think about SETI. The search for extraterrestrial intelligence is not the same as the search for extraterrestrial visitors. Physical visitors are almost certainly not coming. Signals might be a different story. Whether signals are being sent is unknown. Whether we are looking with sufficient sensitivity in sufficient directions across sufficient frequency ranges to have a good chance of detecting them is unknown. Whether we would recognize them if we detected them is a non-trivial question. But the physics does not forbid them. That is the crucial distinction. Let us now talk about what different types of alien civilizations might look like given these constraints, about how the impossibility of fast interstellar travel shapes what any civilization can be and do over long timescales. A civilization that cannot travel between stars faster than roughly 1% of the speed of light, which is probably a reasonable upper bound for anything achievable by chemical or nuclear propulsion, spreads through the galaxy slowly, if at all. The timescale for spreading even to the nearest 1,000 star systems is on the order of millions of years at this speed. The timescale for spreading across the full galaxy is hundreds of millions of years. This means that any civilization that has been technological for less than, say, 100 million years has almost certainly not spread significantly beyond its home star system, regardless of how advanced its technology is in other respects. By comparison, Earth has had technological civilization for approximately 100 years. Modern humans have existed for approximately 300,000 years. Complex animal life has existed on Earth for approximately 500 million years. The Earth is 4.5 billion years old. If we imagine the full range of civilizations that might exist in the galaxy, from those that emerged 5 billion years ago around the first generation of sun-like stars, to those emerging now, the ones that emerged earliest have had the most time to spread. a civilization that emerged 5 billion years ago and maintained continuous technological capability, could, in principle, have sent generation ships to every star in the galaxy by now. The absence of such a civilization, the absence of any evidence that any star in the galaxy has been modified, colonized, or used as a base by an extraterrestrial civilization, is one of the most striking facts about our universe. Either very old technological civilizations are extraordinarily rare, or they do not expand into the galaxy at rates that would produce detectable signatures, or they collapse before spreading significantly. The physical impossibility of fast travel makes the second option more plausible. Spreading at even 1% of light speed requires extraordinary and sustained commitment of energy and resources. A civilization might develop technology and then find that interstellar expansion is simply not worth the cost, that the energy required to send generation ships to neighboring stars is better spent on other priorities. This is the scenario in which the galaxy contains many civilizations, each confined to their own star system, not by choice, but by economics, by the calculation that the energy cost of interstellar expansion exceeds the benefit. Not because the physics is impossible, but because the opportunity cost is prohibitive. If this is the common pattern, then the galaxy is an archipelago, thousands of inhabited islands separated by impassable oceans. Not literally impassable, but effectively so at any timescale relevant to civilization. And each island, each inhabited star system, is alone, with its own knowledge, its own history, its own questions. Looking at the same galaxy, discovering the same physics, arriving at the same constraints, and sitting with the same uncertainty about whether anyone else is out there. Let us now talk about something that is both philosophically rich and scientifically grounded, about what the constraints we have been discussing imply for the probability that humanity will ever make confirmed contact with another civilization. Contact can mean different things. Physical contact, a visitation or meeting in person, requires overcoming the travel barriers we have spent the last hour discussing. Given the physics, physical contact from any civilization more than a few hundred light years away is effectively ruled out on any timescale relevant to human civilization as it exists today. Even nearby civilizations could only reach us via slow generation ships taking millennia. Signal contact, receiving or sending a detectable artificial signal, is physically possible but depends on the alignment of many uncertain factors. Are civilizations transmitting? Are they transmitting in frequency ranges we are monitoring? Are they within our detection range? Are we looking in the right direction? Have they been transmitting long enough that their signal has reached us? Artifact contact, finding evidence of a past interstellar civilization in the solar system or nearby space, in the form of probes, structures, or other physical artifacts, is physically possible, but would require that a civilization specifically directed resources toward our solar system at some point in the past. Of these three, signal contact is the only one that seems plausible on timescales shorter than many millennia given current physics, and it depends on choices made by other civilizations about whether to transmit, choices we know nothing about. The probability of contact in the next 100 years is genuinely unknown. It depends on variables we cannot measure: how many civilizations exist within signal range, whether any are transmitting, whether we are looking in the right way. Our current searching capacity is genuinely limited. We have scanned millions of star systems, but in narrow frequency ranges and for limited durations. The parameter space of possible signals is vastly larger than what we have covered. The probability of contact in the next 10,000 years is similarly unknown, but is bounded below by zero and above by certainty. If civilizations exist within signal range and are transmitting, 10,000 years of increasingly sensitive searching with increasingly large arrays would likely detect something. The probability of contact in the next million years, if humanity survives and maintains technological capability, begins to approach meaningfully high values. Because a million years of sophisticated searching with technology that can reasonably be expected to improve substantially would cover a large fraction of the detectability parameter space. But a million years is a long time. Whether humanity will exist and be technological in a million years is its own question entirely. Let us now talk about what it means for the Fermi paradox that the constraints we have been discussing apply equally to us and to any other civilization, about how understanding our own difficulty reaching other stars should inform our interpretation of why no one has reached us. We are currently not transmitting a powerful, intentional, wide-spectrum signal toward any particular star system. We have sent a few targeted transmissions, the Arecibo message in 1974, a few others, but these are not continuous, not high power, and not likely to be detectable over any significant distance by technology comparable to ours. We are producing electromagnetic leakage, radio and television signals that have been spreading outward from Earth at the speed of light since the early 20th century. This electromagnetic bubble is approximately 100 light-years across, containing our signals from roughly 1920 to the present. But this leakage is relatively weak and becomes increasingly difficult to detect with distance. A civilization at 100 light-years receiving our 1920 signals is receiving AM radio and early television, not particularly compelling evidence of an advanced civilization, and not particularly powerful. A civilization at 50 light-years is receiving signals from approximately 1974, the year we sent the Arecibo message and the year the first personal computers were being developed. The point is that from the perspective of any alien civilization, Earth is very recently technological, and our electromagnetic presence is weak, limited, and has only been propagating outward for about 100 years. An alien civilization would need to be within 100 light-years and actively looking in our direction to have any chance of detecting us. We are in exactly the same position relative to other civilizations. Any civilization that became technological within the last 100 years is not yet detectable to us electromagnetically. Any civilization that became technological more than 100 years ago but is not transmitting strongly in our direction is not detectable. The window for mutual detection is narrow. Both civilizations must have been technological for at least the same amount of time as the light travel distance between them. Both must either be transmitting powerfully or be close enough for leakage to be detectable. Both must be looking in the right direction, at the right frequency, at the right time. The smallness of this window, the specific combination of conditions required for mutual detection, is one reason why the silence is not surprising, even if civilizations exist within range. The conditions for detection are strict. The probability that all conditions are simultaneously met for any given pair of civilizations is low. Multiply this low probability across the number of pairs in the galaxy, and you can get either a detectable signal or silence, depending on assumptions about how many civilizations exist and how powerfully they transmit. The silence is consistent with either civilizations are rare or they exist, but the detection conditions are not met. This is the fundamental ambiguity at the heart of the Fermi paradox. The silence is informative but not conclusive. It narrows the possibilities but does not eliminate any of the main hypotheses. Let us now talk about the specific technical developments that are most likely to change this picture, about what advances in the next few decades might shift the constraints enough to meaningfully change what is achievable. In propulsion, the most promising near-term development is nuclear fusion propulsion. Controlled nuclear fusion has been pursued for 70 years and remains difficult, but recent advances, particularly in inertial confinement at the National Ignition Facility and in private fusion ventures, suggest that net energy from fusion may be achievable within the next decade or two. If fusion power becomes practical for terrestrial energy generation, it becomes available in principle for spacecraft propulsion. A fusion drive would not achieve the mass ratios required for stars, other than perhaps nearby ones, but it would dramatically improve on chemical propulsion for missions within the solar system and might enable very long-duration robotic missions toward nearby star systems at low fractions of the speed of light. In signal detection, the most promising developments are in the sensitivity and scale of radio and optical telescope arrays. The square-kilometre array, currently under construction in South Africa and Australia, will be the largest radio telescope ever built, with sensitivity vastly exceeding previous instruments. Combined with AI-driven signal processing that can search for anomalies across vast datasets simultaneously, it will cover more of the detection parameter space than all previous radio SETI combined. In the optical domain, new generations of large ground-based telescopes, the Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope, will be capable of directly imaging Earth-sized planets around nearby stars and analysing their atmospheric composition. If any nearby planet has oxygen and methane simultaneously in its atmosphere, a biosignature indicating active biology, these telescopes could detect it, not confirming technological life, but confirming biological life, which would be transformative. The James Webb Space Telescope is already conducting atmospheric characterization of exoplanets, with results coming over the next decade. Its successor, the Habitable Worlds Observatory, recommended by the 2021 Decadal Survey, is specifically designed for detecting biosignatures in the atmospheres of Earth-like planets around Sun-like stars. If built and launched in the 2040s, it would be the most powerful tool ever created for searching for life. None of these developments make interstellar travel faster or easier. They do not change the rocket equation or the speed of light, but they significantly expand our ability to search for evidence of life, biological and potentially technological, at distances ranging from the nearest stars to hundreds of light years. The next 20 to 30 years are likely to be the most scientifically productive period in the history of the search for life beyond Earth. Not necessarily producing positive results, the answer might be that life is rare or that technological civilizations are rare, but narrowing the uncertainty enough to meaningfully shift our picture of whether we are alone. Let us now talk about how what we have discussed tonight connects to the most fundamental questions about the nature of the universe and our place in it. The physical impossibility or near impossibility of interstellar travel is not just an engineering fact. It is a feature of the universe's structure that has implications for the nature of intelligent life within it. In a universe where travel between stars was easy, where the distances could be crossed in days or weeks at low cost, the galaxy would be thoroughly explored and potentially colonized. Any civilization that developed would quickly learn whether others existed. The question of whether life exists elsewhere would be answered definitively within centuries of the first technological civilization emerging. But we do not live in that universe. We live in a universe where the distances are what they are, the speed of light is what it is, the rocket equation is what it is. And in this universe, our actual universe, intelligent life, if it exists elsewhere, is isolated by physics in ways that intelligence itself cannot overcome. This means that every civilization that has ever developed, anywhere in the galaxy, has faced the same situation we face, looking out at a sky full of stars and planets, knowing, or eventually discovering, that life probably exists elsewhere, being unable to confirm it, being unable to reach it, being unable to establish contact on any timescale shorter than centuries. Every civilization that has ever asked the question we are asking, are we alone, has asked it without being able to answer it, has built radio telescopes and listened, has done mathematics to understand the distances and been sobered by the results, has sat with the specific combination of almost certainty and absolute uncertainty that defines our relationship to the question of other life in the universe. This is not a small thing. It is the specific shape of the intellectual and existential situation that intelligent life in this universe occupies. not the triumphant discovery of a galaxy full of neighbours, not the lonely certainty of being the only mind. For something in between that the physics enforces, probable company across uncrossable distances. The universe appears to be structured in a way that makes intelligence isolated by default. Not deliberately, not cruelly, simply as a consequence of the specific values of physical constants and the specific properties of space-time that make up our universe. Different values of these constants and properties might produce a universe where contact was easy, or where it was even more impossible. We happen to inhabit a universe where it is effectively impossible on human timescales, and physically impossible in some cases, but where the existence of others is, probabilistically, almost certain. This is a strange place to be, and understanding it fully, following the physics all the way to its conclusion, rather than stopping at a comfortable abstraction, produces a specific kind of clarity. Not despair, not hope. Clarity. The distances are real. The physics is real. The constraints are real. And within those constraints we exist, one small mind among what are probably many, separated by distances that make contact essentially impossible. Looking at the same sky that every other civilization has looked at, asking the same question they have asked, arriving at the same recognition that the universe is structured in a way that makes the question itself the permanent state. Not a puzzle to be solved and set aside, a permanent feature of what it means to be intelligent in this particular universe. Look up tonight. The stars are there. They have planets. Some of those planets almost certainly have life. Some of that life may have developed intelligence. Some of that intelligence may be looking back in this direction. And the distance between us, 40 trillion kilometers to the nearest star, multiplied by however many inhabited worlds there are, constrained by the speed of light and the rocket equation and the expansion of space-time, is the distance the universe has placed between minds. Real, measured, not metaphorical, and in all likelihood, permanent. For any civilization bound by the laws of physics as we understand them, which is to say, for any civilization in this universe, the stars in the sky are not destinations. They are neighbours, glimpsed across an uncrossable distance. Brilliant, present, unreachable. Let us talk about something that takes the physical constraints we have established and applies them to a specific and often misunderstood scenario, about what would actually happen if a civilization discovered Earth and decided to send a mission here, working backwards from arrival to departure to understand what the physics demands of any would-be visitor. Start at the arrival end. A spacecraft from another star system enters our solar system. It must decelerate. Whatever velocity it was travelling at during the interstellar cruise phase, whether 1% or 10% or 50% of the speed of light, it must shed that velocity to enter orbit around Earth or land on its surface. Deceleration requires the same energy as acceleration. The propellant requirements for deceleration are the same as for acceleration. This means that any spacecraft capable of making a one-way trip to Earth must carry enough propellant for two complete velocity changes, one to accelerate from its home system, one to decelerate upon arrival. If it intends to return, it must carry propellant for 4 velocity changes. The mass ratios compound exponentially with each addition. A round-trip mission at 10% of the speed of light requires a starting mass that is the square of the one-way starting mass for the same payload. Already enormous numbers become incomprehensibly larger. Unless, and this is a crucial alternative that changes the calculation significantly, the arriving spacecraft can refuel at the destination using materials available there. If alien visitors could extract hydrogen or helium from our outer planets, or mine reaction mass from asteroids or comets in the solar system, they could eliminate the need to carry return propellant from home. This dramatically reduces the launch mass required. But extracting and processing propellant in an unknown solar system requires infrastructure. Either the arriving spacecraft carries the equipment to build that infrastructure, adding mass to the already massive spacecraft, or it is preceded by automated probes that establish the infrastructure before the crewed or even substantial robotic mission arrives. The most rational approach for any civilization attempting interstellar travel, given the physics, is not to send a single large crewed spacecraft. It is to first send small, fast probes, precisely the breakthrough Starshot model, that arrive early, survey the destination, assess resources, and transmit findings. Then, if the destination proves worthwhile and resources are available, a larger and slower mission follows to actually establish a presence. This means that any interstellar-capable civilization visiting Earth would likely have gone through a multi-stage process. First small probes, then assessment, then a larger mission if warranted. The probes would have arrived decades or centuries before any substantial mission. Their signals, transmitted back at the speed of light, would have been received by the home civilization years or decades after the probe's arrival. The home civilization would then have had to make a decision about whether to send a larger mission, plan it, build it, and launch it, a process taking decades or centuries more. The minimum time from first detection of Earth as a potentially interesting target to arrival of a substantial mission is therefore not just the travel time. It is the travel time of a fast probe, plus the communication delay for information to travel back, plus the planning and construction time, plus the travel time of the larger mission. For a civilization at even 10 light-years distance, this minimum is measured in centuries. This illustrates that interstellar missions are not impulsive decisions. They are civilizational commitments made on timescales comparable to the rise and fall of empires. Any civilization that arrived here would have been planning, building, and traveling for a very long time. Longer, in most cases, than the entirety of recorded human history. Let us now talk about what that level of commitment implies about the civilizations that could potentially make such a trip, about what kind of society could sustain a multi-century, multi-generation project with no guarantee of success and no ability to receive updates from the destination until the mission arrives. The psychological and sociological challenges of an interstellar mission are as profound as the engineering ones. A generation ship carrying crew at 0.1% of the speed of light to Proxima Centauri would take approximately 4,000 years to arrive. During those 4,000 years, the crew would live, have children, teach those children, who would have their own children, across perhaps 160 to 200 generations. No one alive at departure would live to arrive. No one alive at arrival would remember departure, except through transmitted history and cultural memory. The mission's purpose, reaching another star system, would need to be maintained as a cultural imperative across 200 generations. Not just remembered as history, actively maintained as the defining purpose of the community. Every generation would need to teach the next that the mission is the reason for the ship, for the community, for all the choices and sacrifices of life aboard. The history of human institutions does not inspire confidence about maintaining focused purpose across 200 generations. The oldest continuous human institution is arguably the Catholic Church at approximately 2,000 years. The longest continuous political entity is possibly the Japanese imperial line at perhaps 2,600 years in some form, though with substantial changes in actual function. These are exceptional. Most civilizations change beyond recognition within a few centuries. A generation ship culture would need to be more stable than any institution in human history, for 4 times as long as the longest running institutions we have, under conditions of extreme physical confinement, with no external contact and no possibility of resupply or rescue. What kind of culture could sustain this? What kind of governance? What kind of religion or philosophy that kept 200 generations focused on the same mission without either collapsing into short-term thinking or fragmenting into factions with different priorities? We do not know. Humanity has never had to sustain a focused civilizational purpose across 200 generations under these conditions. We can imagine the requirements: strong cultural identity, robust institutional memory, probably some combination of genuine belief in the mission's importance, and structural incentives that make maintaining the mission individually rational for each generation. But imagining the requirements is not the same as knowing they can be met. The generationship problem is not just an engineering problem. It is a sociological and psychological and philosophical problem of comparable or greater difficulty. Any alien civilization that has actually sent a generation ship to another star system has solved this problem. Whatever they are, whatever their biology, their psychology, their social organization, they have found a way to maintain civilizational purpose across timescales that would transform human civilization beyond recognition. Understanding what they are and how they did it might be as interesting as anything they know about science or technology. Let us now talk about the energy problem from a different angle, not from the perspective of what it costs to accelerate to interstellar speeds, but from the perspective of what civilizations actually have available and how that budget compares to what interstellar travel requires. A Type 1 civilization on the Kardashev scale is one that has harnessed the total energy available on its home planet, all incident solar radiation plus geothermal and other sources. For Earth, this is approximately 1.74 times 10 to the 17th power watts, roughly 100,000 times current human energy consumption. Humanity is currently somewhere around 0.7 on the Kardashev scale. A Type 2 civilization harnesses the total energy output of its star. For a Sun-like star, this is approximately 3.8 times 10 to the 26th power watts, 1 billion times more than a Type 1 civilization. The canonical mechanism for achieving this is a Dyson sphere, a structure enclosing the star and capturing its entire output. A Type 3 civilization harnesses the total energy output of its galaxy, roughly 10 to the power of 37 watts for a galaxy like the Milky Way, another 10 billion times more than Type 2. These classifications were proposed by Kardashev in 1964 as a useful way to think about the energy scales available to civilizations at different stages of development. They are not physical laws. Civilizations need not follow this specific progression, but they provide a useful frame for thinking about energy availability. What do interstellar mission energy requirements look like against this scale? Accelerating a 100,000 kilogram spacecraft to 10% of the speed of light using perfect matter-antimatter propulsion requires approximately 4.5 times 10 to the 20 joules of propellant energy, about 3 times Earth's current annual energy consumption. A Type 1 civilization could, in principle, provide this energy, but the propellant, the antimatter, must be produced first. Producing 210,000 kilograms of antimatter at current production efficiencies would require an energy input of roughly 10 to the power of 37 joules, comparable to the entire annual energy output of the Milky Way. Even at 100% efficiency, producing this much antimatter from energy requires 10 to the power of 37 joules, which is Type 3 civilization territory. This comparison is stark. Providing the kinetic energy of the mission is a Type 1 problem. Producing the antimatter to achieve that kinetic energy efficiently is a Type 3 problem. The discrepancy is 17 orders of magnitude. This is why matter-antimatter propulsion, while physically the most efficient known propulsion mechanism, is not practically achievable without a scale of energy production that is beyond anything in our foreseeable future. A civilization would need to be collecting and converting stellar output to produce antimatter in these quantities. And even at that scale, production would take millions of years. Nuclear fusion propulsion is more accessible. Deuterium and helium-3 fusion, used as propellant, would require collecting fuel from a planetary system's outer planets and gas giants, achievable in principle by a civilization with a strong presence in its own planetary system. The mass ratios for fusion propulsion at modest fractions of light speed are more manageable than chemical rockets, but still formidable. The Daedalus study, conducted by the British Interplanetary Society in the 1970s, the most technically detailed interstellar spacecraft design ever seriously attempted, proposed a two-stage unmanned fusion pulse drive spacecraft capable of reaching Barnard's star at 12% of the speed of light in approximately 50 years. The projected mass was approximately 54,000 tons, 54 million kilograms, of which approximately 50,000 tons was fuel. The study concluded the mission was physically possible within known physics, but required industrial-scale deuterium and helium-3 extraction from Jupiter, a technology several centuries ahead of current capability. Daedalus was for an unmanned probe, scaling to a crewed mission with life support, habitation, and enough resources for actual scientific work at the destination adds orders of magnitude to the mass. This is the engineering reality of interstellar travel at currently conceivable levels of technology. Unmanned probes are plausible within a few centuries of development. Crewed missions require centuries or millennia more. Both require energy and material resources dwarfing anything humanity currently produces. Any alien civilization that has done this has solved not just the physics, but the industrial and logistical problems of harnessing stellar-scale resources. They are, by definition, a civilization more advanced than us by a significant margin, not just in science, but in their practical command of the physical resources of their star system. Let us now talk about what happens in the other direction, about the specific question of whether humanity could ever become an interstellar civilization, and what the physical constraints imply about that trajectory. The pathway to interstellar capability runs through the solar system. A civilization cannot send generation ships to other stars without first having the ability to travel within its own planetary system cheaply and reliably. The infrastructure, the materials, the propellant, the experience, all of these develop through solar system exploration and eventually exploitation. Humanity is at the very beginning of this process. We have visited every planet with robotic spacecraft. We have placed humans on the moon. We are developing technology for crewed Mars missions within this century. The next steps, establishing permanent presence on Mars, mining the asteroid belt, operating in the outer solar system, are not technologically out of reach. They are expensive and difficult, but they are extensions of what we already know how to do. They could be achieved within centuries given sustained commitment. From a permanent Mars presence, the outer solar system becomes more accessible. From the outer solar system, the resources of the giant planets become available, including the deuterium and helium-3 that would be required for fusion propulsion. From there, the construction of fusion-powered spacecraft capable of the first interstellar probes becomes conceivable. The timeline for all of this is long. A conservative estimate for humanity's first interstellar probe, a small unmanned mission to Alpha Centauri, might be 200 to 500 years from now, assuming continued technological development and commitment of resources. The breakthrough Starshot concept could compress this dramatically if the engineering challenges prove tractable. A crewed interstellar mission is much further out. The mass requirements, the life support challenges, the generational continuity problem. These push a crewed mission to another star into the range of centuries to millennia from now, under any realistic technological trajectory. What would it take to compress this timeline significantly? Either a breakthrough in propulsion physics, some discovered mechanism for producing thrust more efficiently than anything currently known, or a breakthrough in the speed of technological development, perhaps through advanced artificial intelligence, designing and building systems far faster than human engineers could. Neither of these is guaranteed. The history of physics is not one of regular breakthroughs appearing on demand. The history of technology is not one of continuous exponential acceleration. Both have periods of rapid advance and periods of plateau. Whether AI-driven design acceleration will produce the specific breakthroughs needed for interstellar propulsion is unknown. What is known is that the physical constraints are real and specific, the targets are clear, the parameters required for interstellar travel are well defined by the rocket equation and the laws of relativity. Progress toward those parameters is measurable, and humanity is, very slowly and imperfectly, moving toward them. Let us now talk about something that adds a layer of philosophical complexity to the entire discussion, about the question of whether physical travel to another star is actually the right goal, or whether there are other ways of achieving what we are actually after. What do we want from contact with another civilization? At the most fundamental level, we want information. We want to know whether life exists elsewhere. We want to know what other forms it takes. We want to know whether other intelligences have developed technology. We want to know what they have learned and experienced and discovered. Physical travel provides access to that information in the most complete possible way. Direct observation, physical interaction, sample collection, conversation. But physical travel at interstellar distances is so difficult that pursuing it for the purpose of information exchange seems like using the most expensive possible means to achieve an end that might be achievable another way. Signal contact, electromagnetic communication, provides information at the speed of light, at tiny cost compared to physical travel, with delays measured in years rather than millennia. The information is less complete than physical contact. You cannot collect samples via radio, but it is vastly more achievable. If what we actually want is to know whether other intelligences exist and what they have learned, the efficient path is to invest in signal detection rather than spacecraft development. Build the largest radio telescope arrays feasible. Build the most sensitive optical SETI instruments. Develop the AI tools to search the resulting data streams for anomalies. Cover the maximum possible fraction of the signal detection parameter space. Go outside tonight. Find a dark patch of sky, away from streetlights if you can, and look up. Pick a star, any star, the bright one to the south, the faint one near the horizon. It doesn't matter which. That star is a sun. It is burning right now. Nuclear fusion in its core, converting hydrogen to helium, releasing energy in the form of light that left the star years or decades or centuries ago and just now landed in your eyes. The light is real, the star is real, the distance is real. Now ask, could anyone from that star reach us? Follow the physics. The nearest star is 4.24 light-years away, 40 trillion kilometers. Our fastest spacecraft would take 73,000 years to cover that distance. At a velocity of 1% of the speed of light, far beyond anything on our technological roadmap, the journey takes 424 years. The energy required to accelerate even a small spacecraft to that velocity exceeds the total energy consumption of human civilization for years. The propellant required, if using matter-antimatter annihilation, would take millions of years to produce at any foreseeable production rate. And that is the nearest star. The star you are looking at right now is probably not the nearest star. It is probably tens or hundreds of light years away. The light reaching your eyes left it before you were born, before your parents were born, possibly before the United States existed as a country. At 1% of the speed of light, traveling from a star 100 light-years away takes 10,000 years. 10,000 years is the entire span of human civilization, from the earliest agricultural settlements to the present day. A spacecraft launched from that star when the first cities were being built in Mesopotamia would be arriving now. And traveling at 1% of the speed of light requires energy and engineering that would be extraordinary by any standard we can currently conceive. The rocket equation does not care about ambition. It is a relationship between velocity, exhaust speed, and mass ratio. and it is merciless. To go faster requires exponentially more propellant. To carry more propellant requires a bigger spacecraft. A bigger spacecraft requires more fuel to accelerate. The numbers compound in ways that rapidly become incomprehensible. The interstellar medium, the thin gas filling the space between stars, is not empty. At velocities approaching meaningful fractions of the speed of light, individual hydrogen atoms hit a spacecraft with the energy of cosmic ray particles. The leading face of any fast-moving spacecraft is being bombarded by a continuous stream of radiation. Any material we know how to make would erode. Any crew would need extraordinary shielding. Special relativity helps. Time dilation means travelers would experience less time than external observers. But time dilation does not reduce the energy required. It merely compresses the traveler's subjective experience of a journey that still consumes enormous energy and crosses enormous distances. And for civilizations beyond our cosmic event horizon, beyond approximately 16 billion light-years, the universe's own expansion makes contact not merely difficult, but physically impossible. Space between us and those civilizations is expanding faster than light. No signal, no spacecraft, no information of any kind can cross that gap. Those civilizations are permanently, physically unreachable. Not because they are too far, because the structure of space-time itself makes the distance uncrossable. This is the universe we actually inhabit. Not the universe of science fiction, where faster-than-light travel is routine and the galaxy is a neighborhood. The real universe. The one with the specific speed of light, the specific rocket equation, the specific expansion rate driven by dark energy, the specific distances between stars. In this universe, the stars in the sky are not destinations that other civilizations can simply choose to visit. They are places separated from each other by distances that, at any velocity achievable within known physics, require timeframes measured in human generations, civilizational lifetimes, geological epochs. For a civilization to send visitors to Earth, they must first be aware that Earth is worth visiting, which requires detecting our electromagnetic emissions, which only extends a few hundred light-years. They must then build spacecraft capable of the journey, and acquire the energy and materials to fuel it. They must sustain the mission across timescales longer than any human institution has ever maintained its original purpose. And the crew, or their descendants many generations removed, must arrive at a destination they have never seen, that their ancestors chose for them after a journey that consumed centuries. This is not impossible, given enough time, enough resources, enough commitment, but it is hard in a way that makes it extraordinary rather than routine. Hard in a way that should make us question whether it has happened at all. The silence we observe is not conclusive. It does not prove we are alone. The searches we have conducted have covered a tiny fraction of the parameter space. There may be signals we have not detected. There may be visitors we have not recognized. The universe is large and our knowledge of it is incomplete. But the silence is consistent with the physics. A universe where interstellar travel is this difficult would produce silence. Not because no one is there, but because getting here from there is so hard that visitors would be extraordinarily rare and in some cases physically impossible. Every star you see tonight is burning. Most have planets. Some of those planets are in the right temperature range for liquid water. Some fraction of those may harbour life. Some fraction of that life may have developed intelligence. Some fraction of that intelligence may be looking at its own sky right now, at the stars it cannot reach, asking the same questions we ask. And the distances between us and them are the same distances, the same physics. The same speed of light, the same rocket equation, the same expansion of space-time. They cannot come here, not easily, not quickly, not on any timescale that has meaning in the context of a single civilization's existence. And we cannot go there. The universe has placed us in the same condition it has placed every civilization that has ever existed in it, surrounded by evidence that we are probably not alone, with no reliable way to confirm it, separated from any potential companions by distances the laws of physics make effectively uncrossable. The stars are there, brilliant, burning, real, and the distance between us and them is the distance the universe has decided to place between minds. Not as punishment, not as design, simply as consequence, as the result of the specific values of the constants that define this particular universe: the speed of light, the strength of gravity, the amount of dark energy, the distances between stars. We live in those distances. We measure them. We calculate what they imply. We understand, with more precision than any previous generation of humans, exactly how large the gaps are and exactly what the physics says about crossing them. And then we look back up at the stars. Still there, unreachable, but not, probably, uninhabited. That particular combination, almost certainly not alone, almost certainly unable to confirm it, almost certainly unable to make contact in any time frame shorter than centuries at best, is the specific existential condition that intelligent life in this universe occupies. All of it, everywhere, looking at the same sky, discovering the same constraints, sitting with the same silence, the same stars, the same distances, the same unanswered question.